In the previous section, we discussed how we can find maxima and minima for multivariate functions. In this section, we want to do something similar. We want to find the maximum and minimum of some multivariate function. So we could write that multivariate function as z equals f of xy, but we want to set it subject to a constraint. Which we will represent as setting some other function equal to 0. Okay. This has some good real life application. So imagine you're running a business. Okay. Now you want to maximize your profit. Maybe this is your profit function. You want to maximize your profit. But you can't just make however many of product X and however many of product Y you want. You have only a limited number of factories, only a limited number of capacity. So if you make more of product X, maybe you have to make less of product Y and vice versa, right? There are constraints on how much product you can actually produce and sell. You want to maximize your profit subject to those constraints. Okay, so you could see why this question could be a useful one. So let's think about this graphically. It'll help us to figure out a way to approach this sort of problem. Okay, so here is our function. This is the function that we want to maximize, right? But we are subject to a constraint. This curve along the surface represents our constraint. We want to maximize the function value, but along this constraint function. We have to stay on this constraint function. All right. Now, just eyeballing it, you could kind of see where the maximum value would be, right? It'd be right around here. That's where that constraint function gets to be the highest on the surface, right? That's where it reaches the highest value. Okay. Now, if you stare at this long enough, you may realize something very interesting. Where it reaches that highest value is going to be tangent to a level curve of the surface. Okay, so if I draw some level curves of the surface here, remember a level curve is just where the function value is equal to a constant. Okay, so here are several level curves to the surface. Now, this, if we look at overhead, it's really clear that our constraint is tangent to one of the level curves. Why is that? Well, if you think about it, where you reach your maximum must be the highest value of z that constraint equation reaches, right? That's the maximum value. Okay, so you must go right and approach that level curve, and then you have to go back down. Because if we go past the level curve, that means we're going to higher function values, higher values of z. We're going further up the edge of this surface. Okay, so this is just one very interesting observation, that the point where we reach the maximum value on our constraint equation is tangent to one of the level curves. It's not immediately clear for any general problem which level curve, but we can see that we would be tangent to one of the level curves. Okay, and this gives us a hint for how to approach this problem, because the direction right at that point where we reach the maximum value, the direction of the constraint equation and the level curve that we're tangent to, it's in the same direction at the same time, right? So if we could find a way to describe that directionality, then that gives us a way to figure out where we might have an absolute maximum, right? Because where our constraint equation matches up is tangent to a level curve, that could be a local maximum or a local minimum. Okay, so what we're going to do is we are going to use the gradients. Okay, remember the gradient of a surface points orthogonal to the level curves. Okay, the gradient of a surface at a point points orthogonal to the level curves because it points in the direction where the surface increases the fastest, where it is steepest. Okay, and that means you want to rush away from a constant level as fast as possible. The level curves are where you stay flat, where you stay constant. The gradient points in the direction where you increase the fastest. So you want to get away from that constant value as quick as possible. So your gradient will always be orthogonal to your level curves. But because the constraint equation and the level curve are tangent to each other, that gradient will also be orthogonal to the constraint equation. So if I can find another vector that's orthogonal to the constraint equation, it should be pointing in the same direction, right? So the idea here is to take the constraint equation. Remember how we think about the constraint equation. It's a function of two variables, but it's equal to 0. So it's kind of a level curve of this function g of xy. The constraint equation is itself a level curve, right? So if we think about that here, means we can think about all these level curves, and we're only interested in one of them. But because the constraint equation is itself a level curve, we know that gradients are orthogonal to level curves. So I can take the gradient of that function g. I can take the gradient of that function g, and it should be pointing orthogonal to our level curve. Should be pointing orthogonal to the constraint equation. Okay, so I will get two vectors that are both orthogonal and pointing in the same direction at the same point. And that only happens if the constraint equation is tangent to a level curve. And that tells us that this might be a good place to look to find an absolute maximum or an absolute minimum. Okay, so that's the idea. That's the idea of what's going on. All right, so how does that translate here? So the gradient of this at whatever point our maximum or minimum is at should be pointing the same direction as the gradient of the function of our constraint equation. Okay, now they don't have to be the same length. These two vectors, this vector and this vector, don't have to be the same length, but they should be pointing the same direction, which means they should be scalar multiples of each other. So there should be some scalar lambda so that this equation holds true, so that they're scalar multiples of each other. Okay, this happens when we reach a maximum or minimum value of our function along our constraint equation. Okay, so this is a condition we want. If we satisfy this condition, it may mean that we are that we have a maximum or minimum value at that point. Gives us a place to check. Okay, this scalar multiple here is the Greek letter lambda. Lambda is the Greek equivalent for L, the letter L. Okay, that is our Lagrange multiplier. That's where we get the name for this section. Okay. Now, this will actually give us one more variable than we have equations, so we need one other piece of information to be able to solve this, and that is our original constraint equation. Once we take the gradient, we lose any information that it was equal to 0, right? This was equal to 2 or 17 or whatever. Once we take the gradient, the derivative of that constant goes away. Okay? So we need this extra piece of information. So the idea of this section is we're going to set up this system of equations and we will solve this system of equations. Solve this system of equations. Any xy solution to this system is a candidate for the maximum, I should say the location of the maximum or minimum value of the function subject to the constraint. And that's because any xy solution to this system, since the gradients will be scalar multiples of each other, that means that we found a place where the level curve and the constraint are tangent. And we want to make sure we're focused on the particular constraint we are interested in. Okay? So this tells us all the places on this constraint where the constraint curve and the level curves of our function that we're trying to maximize or minimize are tangent to each other. And if they're tangent, that might mean we've reached a maximum value or a minimum value. Once we've found them, just because we find it, by the way, doesn't mean for sure it is the location of a maximum and minimum value. But what we could do then is we can plug them into our original function and find which values give us the highest values, what gives us the lowest values. And that will allow us to find our maximum and our minimum values. Okay? So let's take a look at an example. We want to use the method of Lagrange multipliers to find the maximum and minimum values of the function 4xy subject to the constraint x squared over 9 plus y squared over 16 equals 1. Okay, so along this ellipse, where does this function reach its maximum? Where does it reach its minimum? Okay, so using the method of Lagrange multipliers, what we're going to do is we're going to set up a system of equations. Okay, the first vector equation would be the gradient of f, that f, the function we are trying to maximize or minimize, should be equal to some scalar multiple lambda times the gradient of g, where g is our constraint equation. So this is our constraint equation here. Okay, now what we want to do, traditionally, we set it equal to 0. So I'm going to take this, let me take it and move it over here. So our constraint equation would be x squared over 9 plus y squared over 16, and I'll just subtract the 1 over, and we're interested in particular when that function is equal to 0. That is our constraint. All I did here is I just moved this 1 over so that we have the way we traditionally express the constraint equation. Some function equal to 0. Okay, so this is our g of xy. And then we need one other equation, and that is the constraint equation itself. Okay, we want to solve this system of equations. Now, of course, to do that, we first should find the gradient of f and the gradient of g, see what we're dealing with here. Okay, so the gradient of f, so I'm going to start by taking the partial derivative of f with respect to x. If I take the partial derivative with respect to x, I get 4y, and the partial derivative with respect to y, I get 4x. Okay, and then let's take the gradient of g. So this is my function g. So the gradient of g, so partial derivative of g with respect to x, I get just 2/9 x, right? Partial derivative with respect to y, I get 2/16 y, or if I simplify, 1/8 y. Okay, so I'm going to plug this in here, and I'm going to plug this in here. So that means our system of equations becomes gradient of f is 4y, 4x equals my Lagrange multiplier lambda times the gradient of g, which is 2/9 x, 1/8 y. And then I have the constraint equation itself, x squared over 9 plus y squared over 16 minus 1 equals 0. Okay? Now, this vector equation, we could actually split it into two equations by setting the first components equal and the second components equal to each other. Okay, so let's go ahead and do that. So if I do that, give myself a little more room there. On the left-hand side, first component is 4y, and on the right-hand side, if I multiply the scalar multiple lambda in, the first component becomes 2/9 lambda x. Okay, now equate the second components, 4x on the left side, and multiply that lambda in, I get 1/8 lambda y. And finally, I do have still that constraint equation. And I'm going to go ahead and move the 1 over to the other side again. Okay, we traditionally set it equal to 0, but this is a little more practical to work with. Okay, so this is the system of equations I want to solve. Notice I end up with 3 unknowns, x, y, and lambda, and I have 3 equations. Okay, so I should be able to solve this exactly. Notice, first off, I'm only actually interested in the x and y. So we don't need to find the lambda, though sometimes it's useful to do so. Also, this system of equations is not linear. So using something like substitution probably won't work here. Okay, I'm sorry, using a method like elimination or addition, that won't work here. We need to use substitution for non-linear systems of equations. All right? Now, if you don't know where to start, a good place that I like to start with is isolating lambda in your constraint in these two equations. Okay, and then setting them equal to each other. Okay, so if I isolate lambda in this first equation, I would get lambda equals, so I'm going to divide by 2/9 or multiply by 9/2. I'm going to divide by x. If I simplify the coefficient, I'd be left with, I'd get 4 times 9/2. That leaves me with 18. Y in the numerator divided by x. Okay, that's that first equation. Let's solve for lambda in the second equation. Multiply the 8 to the other side, divide by the y. I'd get lambda equals 32x divided by y. Now, it's important to note that we've made an assumption here. By solving for lambda, we assumed that we could divide by x and that we could divide by y. We assumed that x and y are not 0. We don't have any evidence right now to tell us that that's not true. So we have to be aware of that, and we have to consider the possibility that they are 0. So this assumes x and y are not 0. Because we're assuming that, and we really don't have any reason to know that they aren't 0, we'll have to go back and check, well, what if they are 0? What happens then? Okay, but for now, we'll continue on with what we've got. Now, both of these are equal to lambda, so they should be equal to each other, right? I will get 18y over x equals 32 x over y. Let's multiply both sides by xy. And I get, what do I get? 18y squared. The x will cancel on this side. And on this side, the y's cancel. So I get 18y squared on the left, 32x squared on the right. Okay. Let's simplify as best we can here. So if what do 18 and 32 have in common? At the very least, they have a 2. So divide everything by 2. I get 9y squared equals 16x squared. And then if you're really clever, you'll notice that if I divide both sides by 9 and divide both sides by 16, I'll get something that'll work real nice with this equation of an ellipse. Okay. You know what? Let me just divide one of them. Let's divide the 9 on both sides. Let's isolate the y. So y squared equals 16/9 x squared. Okay. Or y equals plus or minus 4/3 x, taking the square root of both sides. Okay. All right. So at least we have a relationship between x and y now. We got that using these two equations. Now let's use the remaining equation. Let's plug that in. Okay, so if I plug that in, I'll get x squared over 9. And then instead of y squared, I'm going to get 16/9 x squared, right? Notice I'm plugging into y squared, so I'm going to the equation that tells me what y squared is, instead of going to this equation here. Okay, so y squared is 16/9 x squared, and I divide that by 16. The 16s cancel, so I have x squared over 9 plus x squared over 9 equals 1. So that means I have 2x squared over 9 equals 1, which means x squared is equal to 9/2. If I take the square root of both sides, make sure you consider all the roots, include that plus minus, I get plus or minus 3 over square root of 2. Okay? Now that gives me x. Now what I can do is I could take that x and plug it back in here to find the y. Okay? So, y is equal to, it could be equal to positive 4/3 x. Let's see, this gets a little complicated. You got to be careful here. Y is not necessarily going to be positive at the same time x is positive. Okay, so both signs can change and they don't necessarily change together. Okay, so I'm plugging in x and it could be either positive 3 over root 2 or negative 3 over root 2. Okay, and then when I plug it in, I want to consider all possible y. So y could be plus or minus 4/3 x, and x could have two different signs, right? So y is going to be equal to plus or minus 4/3, and then x is plus or minus 3 over root 2. Okay, the 3's cancel. The signs, well, if they both happen to be the same signs, I'll get a positive. If they're different signs, I'll get a negative, right? So it stays plus or minus. It could be positive or it could be negative, okay? And then I get 4 over root 2. All right? So what that's done for me is it's told me what all my x's and y's can be, okay? My x's could be plus or minus 3 root 2. My y's could be plus or minus 4 root 2. Assuming that x and y are not 0. We still have to consider what if they are 0. Okay? But it gives us some places to work with. Okay? So points to check. X could be positive 3 over root 2, or it could be negative 3 over root 2. Okay? Now, y could be positive 4 over root 2, or it could be negative 4 over root 2. Notice I'm looking at all the combinations of x and y's that might work here. Okay? The x could be positive or negative. The y could be positive or negative. But they don't necessarily have to be positive or negative at the same time. So they could both be positive. The x could be positive. The x could be negative. The y could be positive. The x could be positive. The y could be negative. Or they could both be negative. I need to make sure I consider all possibilities. All right. Now, speaking of all possibilities, when we divided by x here, when we divided by y here to the other side, you cannot divide by 0. So we made an assumption that they are not 0. But what if they are? Okay. So if either one of them is 0, we might have problems. So now, let's consider the x equals 0 case. Here we considered the case where x and y are both not 0, right? So if either one of them is 0, if only one of them is 0, then that's a separate case. So right now I'm assuming x is 0. I'm not thinking about what y is. Okay? So let's look at the x equals 0 case. And I'm going to grab this equation. 4y equals 2/9 lambda x. What was it? 4y equals 2/9 lambda, and then I'm assuming x is 0. Well, if x is 0, that means 4y has to be 0. If 4y is 0, that means y has to be 0. So the point would have to be 0, 0, right? But we've only checked one equation. We need to make sure it solves all the equations. So it solves this equation. Okay. It also solves this equation, right? If I plug in 0 for x and 0 for y, that would work. But does it solve this equation? It does not. If x and y are both 0, then the left-hand side of this equation would be 0. It would not be equal to 1. So 0, 0 is not a solution to the system. Okay, so it's not a point we should consider. So what about the case where y equals 0? We've only looked at the case where x equals 0. So if y equals 0, it's much the same situation. Okay, now I'm going to look at, I'll look at this equation, because if y equals 0, it gets rid of this complicated side, right? So it wipes out the most. So if y equals 0, what's the equation again? 4x plus 1/8 lambda y. 4x plus 1 equals 1/8 lambda times my y of 0. Now, of course, 0 times anything is 0, so this whole right-hand side is 0, which means this could only happen if x is also equal to 0. So we would need y equals 0 and x equals 0, and we have exactly the same situation as before. We've already said that 0, 0 cannot possibly be a solution to the system because it cannot satisfy this last equation. We're only interested in x, y points that satisfy all three equations. Okay? All right. So looking for absolute maximum and absolute minimum, we have restricted ourselves to 4 points. Now what we want to do is plug those back into the original function, f of x, y, and determine if at which point do we reach our maximum? At which point do we reach our minimum? And what is the maximum and minimum? Okay, so now this is calculator work. What was our f of xy? It was 4xy. Actually, that's simple enough that we could probably do it. Clear a little space here. Okay, so all I'm going to do is I'm going to take 4 times the x times the y. So the x times the y here, it's going to be 3 times 4 is 12 in the numerator and 2 in the denominator. So that's going to be 6 times 4 is 24. Okay. And notice it's going to be the same for all of these. The only thing that's going to change is the sign. If I have one negative, I get negative 24. I have one negative here, positive times a negative, negative 24. Here I have two negatives. Two negatives become positive, so I get positive 24. So my absolute maximum is going to be 24. My absolute minimum is negative 24. And in both cases, I reach the absolute maximum. I reach the absolute minimum at two different locations. Okay, so the absolute max is 24 at xy equals 3 over root 2, 4 over root 2, and negative 3 over root 2, negative 4 over root 2. And the absolute minimum of the function restricted to the constraint is negative 24, and that happens at two locations. Happens at negative 3 over root 2, 4 over root 2. And it happens at 3 over root 2, negative 4 over root 2. So that's our final answer. Using the method of Lagrange multipliers, we found our absolute maximum and our absolute minimum values for this function. So let's confirm our results graphically. Right, so this is the function we are trying to maximize and minimize, subject to this constraint. Let me zoom out so you can really see that constraint. Okay. So it is an ellipse. We kind of knew that constraint x squared over 9 plus, where'd it go? X squared over 9 plus y squared over 16 equals 1. Here, this is a better way to write it. We knew it's an ellipse, right? So we shouldn't be surprised that we see an ellipse here. But once we place it on the surface, there are definitely some points that are higher than others, right? And so our two maximum points are right there. I don't know if you could see them. Maybe let me make them a little brighter. Okay. We reach our maximum value at 2 points. There they are. And then our minimums are right there. There and there on the other side. Okay. Let's take a look at another example. Here we want to find the maximum and minimum values of the function 4x cubed plus y squared, subject to the constraint 2x squared plus y squared equals 1. All right. So just as before, we're going to set up our system of equations using Lagrange multipliers. All right. The approach here is that the gradient of our objective function, the function we're trying to maximize or minimize, should be equal to lambda times the gradient of our constraint function. That will make sure that the level curve of this is tangent to our constraint function, which means it might be a maximum or minimum value. And then we actually want our constraint function also. Okay, so here f of xy equals 4x cubed plus y squared. So if I take the gradient of f, partial derivative of f with respect to x is 12x squared. partial derivative of f with respect to y is 2y. Okay, so that will go there. And then our constraint, we usually take this and set it equal to 0. So I'll move the 1 to the other side. 2x squared plus y squared minus 1 equals 0. And so the gradient of g, so this is g, and we're setting g equal to 0, right? We're setting it equal to 0. So the gradient of this, partial derivative with respect to x, I get 4x. Partial derivative with respect to y, I get 2y. Okay, so let's plug in what we have here. Gradient of f, we just calculated, that's 12x squared, comma 2y. And that should be equal to some multiple lambda times the gradient of g, if we want to find the absolute maximum or the absolute minimum. Gradient of g is 4x, comma 2y. Okay, and then we have the constraint equation itself, which is just setting function g equal to 0. So 2x squared plus y squared minus 1 equals 0. And then let's separate out the equations, the components in our vector equation. So first component equals first component. First component on the left side is 12x squared. On the right side, if I distribute that multiplier lambda in, I get 4 lambda x. Okay. And then second component equals second component. I get 2y equals 2 lambda y. And then I have my constraint equation. Writing it like this with a 0 on one side and the 1 over here is kind of a little weird, so I'm going to move the 1 back over. That's the traditional way to write it. There's nothing wrong with writing the 1 over here. Okay, so I'm just writing it, returning to this normal way to write. Okay, this is the system of equations we want to solve. We have 3 unknowns, x, y, and lambda. We have 3 equations. Okay, now what jumps out to me is this equation right here. I've got 2y on this side, I've got a 2 and a y on that side, so what does that mean for lambda? So if I divide both sides of the equation by 2y, I get lambda equals 1, right? Write it this way. Lambda equals, I had the 2y on the one side, I'm dividing by the 2y to the other side, and so that should give me 1. But we're making an assumption there, aren't we? Whenever you divide by a variable, that means you're assuming that variable isn't 0. We don't know for sure that y can't be 0. Maybe one of the possible solutions we need to look at y is 0. By dividing by that y, we would be throwing that possible solution out, and we might miss it. So we got to keep track of that. Okay? This assumes y is not 0. We're going to have to check what happens if y is 0 later. Okay? For now, let's stick with this. So I've got, I figured out lambda equals 1. So let's now use that together with this equation, my other equation with a lambda in it. That would be 12x squared equals 4 times my lambda, which is 1 in this case, times x. So I get 12x squared equals 4x. I'm going to start by dividing both sides by 12. I'm sorry, not 12, 4. Just to tidy things up a little bit. Now, whenever you have an equation like this with x's on one side, x's on the other, and some of those x's are of a higher power, you want to set this equation equal to 0. You want to get it equal to 0. So I'm going to subtract this x to the other side of the equation. And we have several ways to solve a quadratic equation like this. We could use something like the quadratic formula, but this is definitely easier to solve by factoring. So let's factor out an x. I'm left with 3x minus 1. Okay. Now I have two things that are multiplying to give me 0, which means one of them has to be 0. So one possible way this could happen is if x equals 0. And the other way would be if 3x minus 1 equals 0, which would happen if x equals 1/3. Okay, so I have two possible x's. And now what I want to do is I want to plug that into the remaining equation and find what y would go with it. Okay, so 2x squared plus y squared equals 1. So let's start by plugging in x equals 0. I get 2 times 0 squared plus y squared equals 1. That's just y squared equals 1. So y is going to be, if I take the square root, I get plus or minus 1. Okay, so that gives me two possible answers. X equals 0, y equals 1, and x equals 0, y equals -1. So let's keep track. Let's look at our possibles. So x equals 0, y equals 1, x equals 0, y equals -1. Okay? Now what if we plug in this other value? What if I plug in x equals 1/3 into this equation? If I plug in x equals 1/3, then I'm going to get, so that'd be 2 times 1/3 squared plus y squared equals 1. So I get 2/9 plus y squared equals 1. 1 minus, subtract the 2/9 to the other side. Okay, subtract to the other side. 1 minus 2/9, that'd be 9/9 minus 2/9, so that's going to be 7/9. If I take the square root, y is going to be equal to plus or minus √7/3. Okay, so that gives me two more possible answers. When x is 1/3, y could be positive √7/3 or negative √7/3. Okay, so far so good. We have 4 possible places where I might have a maximum or minimum. And we've exhausted this line of reasoning. Okay, but we had to make an assumption, remember. We had to assume that y was not 0. So what if y is 0? We have to consider it. Okay, maybe there are no possible solutions, but we need to consider it. So I'm going to assume y is 0. Now that means this first equation is very boring. I'm sorry, the second equation here, it's very boring. It's just 0/0. So that tells me nothing if y is 0. This equation doesn't have a y in it. So I'm going to go with this third equation because if I plug y into 0 into y there, I will get some useful information. Okay, so I'm going to grab 2x squared plus my y squared, plug in 0 for the y, equals 1. Of course, 0 squared is just 0, so I get, if I solve for the x squared, I get x squared equals 1/2, or x equals plus or minus 1/√2. Okay, now I do need to make sure that it satisfies this equation, but since I could choose whatever lambda I want, I could plug in 1/√2 or -1/√2, and I'll be able to find a lambda that will make it work. Okay, so we found, when y equals 0, we found another possible solution. Okay, we found that when y is 0, x could be 1/√2, or it could be -1/√2. And now We've considered every possibility. We've looked at where y is 0, where y isn't 0, and we found every possible solution in every possible instance. Okay. So now that we know where to look, let's plug it into our function and see where we have our maximum value and where we have our minimum value. All right. So our function here is 4x cubed plus y squared. That's not a terribly difficult function, but I'm going to plug it into a calculator. We have a lot to evaluate. And the cube is actually going to make things a little difficult. I've got a lot of square roots going on, but cubing a square root is just going to make things a little messy. So I'm going to pull up my calculator. And we will evaluate these as quick as we can. All right. So what I like to do is first plug in my function, and that makes it real easy to evaluate. So I'm going to just tell it my function is 4x cubed plus y squared. And so all I need to do now is just say I want f of 0, 1. So that's going to be 1. Let me just do all of them. F of 0, negative 1 is also 1. 1/3, comma, square root of 7 over 3. And same thing, just with negative root 7 over 3. And then finally, 1/2 and negative 1/2. I'm sorry, 1 over root 2. And negative 1 over root 2. Okay, let me plug those in. So this is 1, this is 1, this is 0.92593 about. This is the same. And then I have 1.414 and 1.414. Sorry, negative 1.414. Okay, that means this is our maximum and this is our minimum. Okay, so our absolute max is about 1.414, and it is at the point 1 over root 2 comma 0. The absolute minimum of this function, subject to the constraint, is negative 1.414, and it's going to be at the point negative 1 over root 2 comma 0. And again, let's confirm our results graphically. Pull over the graphing calculator. Okay, so there is our surface, and here is our constraint. So we want to find the maximum minimum values subject to this constraint. So the points we calculated were at 0, 1. That's that point right there. You can kind of see why it was considered, don't you? It was locally the highest point around it. 0, negative 1. Again, locally, it was the highest point around it. And then we had 1/3 and root 7 over 3, 1/3 negative root 7 over 3. Locally, let me zoom in a little bit. Locally, they were the lowest point in their immediate vicinity, right? But the absolute maximum and minimum was 1 over root 2, 0. And it was at negative 1 over root 2, 0. Okay, so we did indeed find the absolute maximum and minimum using the methods of Lagrange multipliers. Take a look at one more example. We want to use the method of Lagrange multipliers to find the absolute maximum of a 3-variable function subject to a constraint. So the process is exactly the same. The formulas are the same. We still want the gradient of f to equal to some scalar multiple times the gradient of our constraint function. We still have our constraint equal to 0. So here, our constraint would be this, but we need it equal 0, so just move the 70 over. 2x squared plus 4y squared plus z squared minus 70. Okay, and we want that equal to 0. And then we need the gradient of g. Now we will have 3 partial derivatives. In fact, we have enough of them that let me give myself a little bit more room and omit the of x, y, z part of the function. Okay, so partial derivative with respect to x is 4x. Partial derivative with respect to y is 8y. Partial derivative with respect to z is 2z. Okay, and then we also have our objective function, the function we actually want to find the maximum or minimum of, subject to the constraint. 3x plus 6y plus 2z. I want the gradient of f for my formula. Partial derivative with respect to x is just 3. With respect to y is just 6. With respect to z is just 2. So plug in gradient of f, 362, equals our Lagrange multiplier lambda times the gradient of g, which is 4x, 8y, 2z. And we're subject to the constraint where g of x, y, z equals 0, so that's going to be 2x squared plus 4y squared plus z squared minus 70 equals 0. And I'm just going to break apart that vector equation. First component on the left side equals first component on the right. Second component on the left equals second component on the right. And third component on the left equals third component on the right. And then finally we have our constraint equation. I'll just move that 70 back to the other side. Okay. Notice that we now have 4 equations and 4 variables, right? Compared to the last couple examples where we had 3 equations with 3 variables. I'm going to approach this starting off pretty much the same. I'm going to assume, wait a second, I forgot to move the 70 to the other side. I'm going to start off by solving for lambda in each case. To do that, I need to assume that x, y, and z are not 0 because I'm going to have to divide by x, divide by y, divide by z in each equation, right? So let's start off by assuming x, y, and z, none of those are equal to 0. Again, as usual, we will have to consider the case that they are equal to 0. Just because we're assuming that they're not doesn't mean that setting one of those equal to 0 won't give us a solution. So we're assuming they're not 0 for now. We'll have to go back and think about what happens if they are 0 later. Okay? So for this first equation, I have 3 equals 4 lambda x. If I solve for lambda, I'd get lambda equals 3 over 4x. For the second equation, if I solve for lambda, divide by the 8y, I get lambda equals 6 over 8y. And this final one, solve for the lambda. I have 2 on the left side, divide by 2z on the right. I get lambda equals 2 over 2z. And I do have a little bit of simplifying I could do, right? 6 over 8y simplifies to 3/4 y. And 2 over 2z simplifies to just 1 over z. Okay? Now all of these are equal to lambda, so they should all be equal to each other. So I have 3 equations now, so I'm just going to pick 2 of them and set those equal, and then pick another 2 and set those equal. And by doing that, I could figure out what's going on one piece at a time. So let's focus on just these first 2. So 3 over 4x and 3 over 4y must be equal because they're both equal to lambda. So 3 over 4x equals 3 over 4y. I'm going to multiply 4y and 4x to the other side and divide by 3. You can probably see I'll get x equals y. Okay, so if x, y, and z are 0, then x has to equal y. Okay, now let's look at these 2, put them together. They're both equal to lambda, so 3 over 4y has to equal to 1 over z. If I multiply z to the other side and y to the other side, I get 3/4 z equals y. And because x equals y, 3/4 z must also equal x. Okay? Actually, let's multiply the 4 to the other side too. So I get 3z equals 4y. I think I like that a little better, although I don't know if it's very useful. Maybe we'll just stick with what we got. Okay? Okay, we've used these 3 equations. Now let's use our remaining equation and try to figure out what's going on. So what I'm going to do, I can plug in x for x. Because y and x are equal, I could plug in x for y. And this will also be equal to x, since x equals y. And I'm just going to move the 3/4 to the other side, so I get z equals 4/3 x. And that way I can swap out z with an expression of x2. And that way I could swap all my variables out and have only one variable left, the x. Okay, so sub in here, 2x squared plus, instead of y, I'm going to swap out for x. So 4x squared plus, and instead of z, I'll plug in 4/3 x. 4/3 x squared equals 70. Okay? So I get 2x squared plus 4x squared, that's 6x squared. Let me go ahead and add those now. So 2x squared plus 4x squared is 6x squared. And then 4/3 x squared, that's 16/9 x squared equals 70. Rather than dealing with the fraction, I'm just going to multiply everything by 9, both sides. 9 times 6 is 54. Plus the 16x squared equals, and I'm seeing where this is going. So I'm not actually going to multiply these. I'll just leave it as 70 times 9. Because I see that 54x squared plus 16x squared gives me 70x squared. And so I'm going to divide by that 70 anyway. So if I divide both sides by 70, I get x squared equals 9, which means x could be plus or minus 3. Okay? All right. We know x and y have to be equal. So our possibles here, let's start listing our possibles. So x could be 3 or it could be negative 3. And I know x and y have to be equal. So if x is 3, then y has to be 3. If x is negative 3, y has to be negative 3. Notice we're not considering, negative 3, positive 3, or positive 3, negative 3, because I know x and y have to be equal. They cannot change signs. They cannot be different signs. And we know that z is equal to 4/3 x. So that means when x equals 3, z is going to be 4/3 times 3. That's just 4. And when x is negative 3, if I plug that in, 4/3 times negative 3 is negative 4. Okay, so that gives us 2 possibles right there. Now I have to think about, what if x equals 0? What if y equals 0? What if z equals 0? Okay, got to think about those separately. So x equals 0 case. Right? Notice it's impossible. Okay, because I would get 3 equals 4 lambda times 0, which is 0, which means I would need 3 to be equal to 0. That's impossible. So x equals 0 can't be a solution. And the same thing's going to happen with y and z. If I plug 0 in for y, I'd get 6 equals 0. If I plug 0 in for z in this third equation, I'd get 2 equals 0. 6 is not 0. 2 is not 0. So those are impossible too, right? So y equals 0 is similarly impossible. Z equals 0 is also impossible. So these are the only two places we have to look, which means one of them better be our absolute max, one of them should be our absolute min. All right, so we're going to plug them into our function, which was 3x plus 6y plus 2z. Numbers are simple enough, I don't need a calculator. So x, y, z, what was it again? 3x plus 6y plus 2z. 3x plus 6y plus 2z. If I plug in 3, 3, 4, 3 times 3 is 9, plus 3 times 6, that's 18. 18 and 9 is 27. Plus 2 times 4, that's 8. So 27 plus 8 is 35. Okay. And if I do negative 3, negative 3, negative 4, notice each component will be exactly the same, but negative. So I'll be getting negative 35. Okay. So my absolute maximum is at 35. My absolute minimum is at negative 35. My absolute max is 35. And it was at the xyz 0.334. The absolute minimum value of the function subject to the constraint was negative 35. And it was at the xyz value negative 3, negative 3, negative 4. I cannot show you a graphical representation of this problem because it's really a four-dimensional problem, right? There are 3 input variables and then 1 output value. And we're not great as humans at visualizing 4 dimensions, so I don't have a tool to show you that. But the math still works. We are able to find an absolute maximum value for the function subject to the constraint and the absolute minimum value for the function subject to the constraint and where those absolute extrema are.